On the screen today we have the Solari Udine clock driver system diagram development. What I'm going to do is take you through the range of system blocks, the functional blocks that are required to achieve the functional requirements that I outlined in the previous video. So the last video is what I wanted the controller to do, and in this video I'm outlining what is needed to make the controller to do those functions. So if we start off with the clock effectively has two inputs. One is time and the other is illumination. The motor is a bipolar motor, and so it needs an H-bridge bipolar motor drive. H-bridge drivers are quite common. They're not made specifically to control a Solari clock, but they have the functionality required to do that. Next is illumination. I'm showing here two blocks that provide 100 milliamps current driver for the LED illumination. And the reason that there's two drivers is because the LED strips that you can buy have A and B strings of LEDs. So they can be driven by having a single LED driver and putting the two strings on the strip of LEDs in series, or they can be driven with two separate LED drivers as I'm showing here. And the reason that I'm planning on using two separate LED drivers is to reduce the voltage output required to achieve the 100 milliamp current. With the LED A and B strings in series, the voltage gets up to over 50 volts, which is a bit high. It also limits the range of devices that can be selected as current drivers. So by having two separate LED drivers, I keep the driver voltage down to about 25 volts. It's much more manageable, and there's a lot more devices that will operate at that voltage level. I'm going to need a means of controlling the inputs to the clock, the H-bridge motor drive, and the brightness of the LED current drivers. And the easiest way to do that these days is with a microcontroller. I've successfully used the ESP32 series in past projects, and that's what I'm going to do for this project. The nice thing about the ESP is that they include both a USB and Wi-Fi Bluetooth options, which is exactly what I need to achieve the functional requirements that I've previously outlined. Now, all of these are going to require a power supply. For the H-bridge bipolar motor drive, I'm going to need a 48 volt power supply. For the LED current drivers, I'll need a supply that can provide 25 volts at least. And for the ESP32 microcontroller, I'll also need a 5 volt or 3.3 volt supply. So I'll need at least 3 power supplies to control the electronic circuitry. But they can't be hooked into the mains. I need a voltage supply to supply all of the power supplies. I need a power supply that sits between the mains power and the 3 low voltage power supplies. So that has to take 240 volts AC in and produce somewhere between 12 and 30 volts output for the converters and the microcontroller power supply. I need at least 4 power supplies. Now, I also wanted a way of monitoring the clock with the microcontroller. And if I'm going to control the LED current in a meaningful way, then I really need to know what the ambient light level is, because that means that I can optimize the clock illumination based on the ambient light level. That only needs to be something really simple, like a light-dependent resistor, which I've already got. My plan is to connect a LDR directly to an ADC input into the microcontroller. One of the functional requirements I want is the ability for the clock to automatically recover if there's a power supply failure or something similar. I really need a method of the clock telling the microcontroller what time is displayed on the clock. And the easiest way to do that is to add a micro switch or similar to the clock, so that at midnight it sends a pulse to the microcontroller saying that is what the time is. And if there's an error, then the clock will make a correction at that point, but potentially the clock could show the wrong time for up to 12 hours. It's an input that I'm planning on including for the microcontroller, but I don't actually have to make the mechanical modification, because this can be a fitted for but not with capability. It's something that is optional. But if I include it in the circuit, it's there. And if I don't include it in the circuit, then it becomes much more complicated to add it further down. In a previous video, I showed how measuring the current indicated the mechanical operation of the clock motor. So I'm going to include the option of measuring the current through the clock motor to determine the health of the clock as a whole. Now the diagram here indicates that that current sensor is going to be inside the clock, and in a way it will be, but it makes sense to include the current sensor functionality with the H-bridge motor drive, because I know already that the candidate drivers that I'm looking at have the ability to measure current flow, and so I'm just going to use the existing capability of those devices to read the current flow into the clock rather than add a separate sensor or other circuitry. If the clock is to recover from a power failure of any sort, then it needs to know what time it is. And there's a range of ways of doing that. What I am going to do is include a battery-back real-time clock device, and that will keep track of the time. So regardless of what happens to the microcontroller, to power supplies or whatever, the actual time will be preserved and available in that real-time clock device. But in addition, because the microcontroller comes with a Bluetooth Wi-Fi capability, I'll be able to make a connection out into the internet and my home network to obtain time from an NTP server, or to obtain time from my Synchronome master clock. I haven't yet developed a circuit to connect my Synchronome master clock to my network, but that's an option that I'll have available with this system. And the capability to get out to an NTP server is already an intrinsic part of my home network. I don't need to add anything. But I also want to add in the option of connecting a GPX U-Blox Neo device. And all I need to do to achieve this is add a 4-pin header that allows a GPS unit to be connected to the serial port of the ESP32 microcontroller. Simply adding a 4-pin header that connects to a GPS unit provides a significant capability because of the amount of information that can be obtained from the GPS unit. I don't plan on fitting a GPS unit, but the addition of a 4-pin header provides that option if I need it in a future application. And the one thing that's left to add to the system diagram is a means of controlling all of this. And the obvious choice is a laptop or a cell phone or a tablet with Wi-Fi or Bluetooth. And that can hook into my home network or even over the internet. That will give me hands-off control and monitoring of not just the clock, but also the entire system. One of the key things to note about the system diagram is that all these different blocks shown are actually pretty simple. There's some power supplies, some very simple basic sensors, a 4-pin header, and not much else. It should also be noted that a lot of the control signals are not shown in this diagram, because if I added all the control signals, this would look like a plate of spaghetti. If you look at the system diagram, the units shown here don't actually achieve the functions that I outlined in the previous video. They are enablers. They enable those functions to be achieved, but the missing part not shown here is the software, and it's the software that makes use of all these different devices to achieve the functionality. The next step in the process is to go through to figure out exactly what components will be used to implement each of the blocks shown in this system diagram. It's going to take me quite a while to develop the circuits to implement each of these blocks in this system diagram. It's going to be a little while before I produce another video on this topic, but it's something that I will be working on. Thanks for watching the video. I hope you look forward to the next video.